In this problem, we're looking at a beam which is clamped on both sides. There's a couple which is applied there at point B, which is 2/3 the way over from the left end. And what we want to do is figure out what the deflection curve is for the beam. Before we start here, I'll say that we're going to replace L over 3 by A. Makes the algebra a little bit easier as we work through. So we're going to start out by making an attempt to come up with our external reaction solutions. So what we know is that this requires us to draw a free body diagram of the entire beam. So we have AY and BY. We have MA and MB. MA and MC. This is actually point C there on the right side. So I will make this force a CY. And then there is this known couple there of MB. So the only thing of the 5 that are shown here in the FBD that we know is MB. So this is a known. So right away we know we're in trouble here because we're going to have far too many unknowns for the equation. But let's find out how bad that it actually is. If I do a summation of moments about A, I got minus MA, the reaction from the wall at A. I have reaction MC there on the right side. I have CY, which has a moment arm of 3A. And let's see, 1, 2, 3, 4. It looks like I'm missing MB, yeah, the applied couple there of MB. So this is going to be equation 1. When I sum forces in Y, I get a fairly simple equation. It says AY and CY must be add up to be a 0. But the downside here is that the problem is indeterminate. At the most, we can write down 2 equations, but yet we have 4 unknowns. We have the reactions, 2 reactions at A, 2 reactions there at C. So it's indeterminate. So we need to come up with our deflection equations, which make up our compatibility equations in the end that tell us what those additional 2 equations are going to be. So I'm going to look at section AB first, which means that I'm going to be drawing a free body diagram of a part of the beam reflecting a cut there between A and B. So this cut is going to happen at some value of X. The FBD that we have here is AY and MA. We have shear force V and bending moment M, and I'm going to call that point C. If I sum my moments about C, what I have here is a minus MA, that's from the wall. I have the bending moment M, which is what I'm trying to find. I have AY, which has a moment arm of X, and it's going to be in the negative Z. So that equal to 0 for equilibrium says that the bending moment in section AB is equal to MA plus AYX. We're all set because now we can say that theta x then is theta on the left hand side plus 1 over EI, the integral from 0 to x of M, and M is MA plus AYX. Well, because we have a clamp condition on the left side, clamp means that not only is the displacement a 0, but so is the rotation, then theta naught is equal to a 0. So we have 1 over EI, MAX, plus 1/2 AYX squared as that. V of x, our deflection, is going to be what it is on the left side, plus the integral of theta, which is 1 over EI, MAX, plus 1 half AYX squared dx. And also again, since the left-hand side is clamped, not only is the rotation a 0, so is the displacement, the deflection. So I get 1 over EI. MAX is 1 half MAX squared plus 1/6 AYX cubed. And then for later use, what I'm going to do here is to figure out what theta and the displacement are for that point there of B. So therefore I'll say that theta B, which is equal to theta at 2A, is equal to 1 over EI 2 MA times A plus that it will end up being 2 AY A squared. So this is going to be my equation 3. And VB, which is the symbol I'm going to use for the displacement at B, or x equal to 2A, will be 1 over EI 2 MA A squared plus 4/3 AY A cubed. So these are two things that come directly from here. I just simply put in x equal to 2a because I know I'm going to need that, because whenever I start my integration up for section BC, those are going to be my boundary condition there on the left hand side. So for section BC, I'll draw a free body diagram of the beam, which is cut somewhere between B and C. So I have AY. I have the couple there of MA. I have the applied couple there of MB. That's unknown. I have the shear force V at that cut and the bending moment M. Let me call that point D. When I do my moments about D, what I'm going to have here is a minus MA. AY is going to have a moment arm of X. X is the distance over to that cut with a negative sign, plus MB, plus the M, which is what I'm trying to find. So therefore, between B and C, the bending moment in that beam is given by the reaction MA, the applied couple MB, and the reaction AY times X. Okay, so we're all set to go then on our integration. So theta x, starting at x equal to 2a, plus 1 over EI, integral from 2a to x of MA plus MB plus AYX dx. Theta 2a, we gave that the name of theta b, which is given there in equation 3. It's going to be 1 over EI. There's going to be an MA plus MB times x minus 2a plus 1 half AY times x squared minus 2a squared, so that's 4a squared, like that. So if I combine my terms together, I get theta b here, 1 over EI. The constant terms are going to be MA plus MB times a minus 2a there. And then we will have another constant term there of minus 2AYA squared. I'm going to have an MA plus MB times x. and I'm going to have a 1/2 ay x squared. I think that's correct. I've got the x squared, I've got the x, I've got the constant terms there. So the integration for v is just an integration of that along with adding the constant there in front, integrating from 2a up to x of theta x. So that's going to be theta b plus 1 over ei minus 2ma plus mb a minus 2ay a squared plus ma plus mb x plus 1/2 ay x squared dx. So I do that integration. We recognize that v at 2a is what we were calling vb, just a different name. So I have a theta b x minus 2a plus 1 over ei minus 2 ma plus mb times a times x minus 2a minus 2ay a squared x minus 2a. I'm going to have 1/2 ma plus mb x squared, so that's x squared minus 2a squared, so that's 4a squared, like that, plus 1/2, oops, not 1/2, there's going to be another factor there in front, because when I integrate x squared, I get 1 over 3, that gives us a 1 over 6 ay x cubed minus the 8a cubed, like that. So these are our two, or this is our equation there for v of x. But please keep in mind we can't quit, because we need to come up with those additional two equations that we had just to solve for the reaction. We got ma, we got mb, we got ay, and we have the other reaction, ay and cy, I guess it is. So what we need to do is now enforce our boundary conditions. So our boundary conditions are that theta at 3a is equal to a 0. There's a wall there. So that gives me theta b plus 1 over ei minus 2 ma plus mb minus 2 ay a squared plus ma plus mb x, and that's equal to 3a plus 1/2 ay times x squared, so that's a 9a squared, like that. So that's one equation. So that's going to be, we're up to equation 5, I think. And then v at 3a, to enforce that boundary condition, it's a 0. So that's vb, which we found back in equation 4. Theta b, this is going to be 3a minus 2a, so that's just a, plus 1 over ei minus 2 ma plus mb a times x minus 2a, that's a, minus 2ay a squared, there's going to be an a there, plus 1/2 ma plus mb x squared, so that's going to be 9a squared minus 4a squared. And finally, the last term, there's 1/6 AY. The cube then is going to be equal to 27 a cubed minus 8a cubed, like that. So this is equation 6. So what we need to do is solve equations 1 through 6 for the unknowns of AY, MA, CY, MC, theta, B, and VB. 6 equations and 6 unknowns. The problem here goes all the way back to the beginning. The problem is statically indeterminate. In order to find our reactions, we're going to rely on equilibrium. Well, equilibrium gave us only 2 equations, and we had 4 unknowns, 4 unknown reactions. We had to pull in at least 2 more equations. So we did so by enforcing our displacements and rotations. On the left side, we said the displacements and rotations are 0. On the right side, they're at C. Displacements and rotations are 0. So that produced us equations 3, 4, 5, and 6, bringing in theta B and VB as unknowns. 6 equations and 6 unknowns. This is the way problems go, which are indeterminate, is that equilibrium only gives you part of the equations. The other ones come from displacements and compatibility, just like we had for the rod and for the shaft.